All right. Well, happy Wednesday. I just posted the PDF for today's lecture, which covers the naive Bayes classifier. I also posted a document of midterm 2 topics. I'll cover the contents of that on Friday, so you will have a good idea of what might appear on the midterm exam. But yeah, that will be coming up because we have a midterm next week, right? So okay. Well, anyway, let's go ahead and take a look at today's lecture. So on Monday, we covered the Bayes classifier, and so just to review how the Bayes classifier works is we apply Bayes' rule, right? We say, probability of A given B is the probability of B given A times the probability of A divided by the probability of B. That's Bayes' rule. And, in terms of classification, we're saying the probability that something belongs to a class, given the data, is equal to the probability of getting the data given that it belongs to a certain class. Okay, and then multiplied by the prior probability that it belongs to that class, divided by the marginal probability of just getting that data regardless of the class. Okay, and we said, for the marginal probability, this exists just so that the sum of the probabilities add up to 1 for all of the different classes. And so we looked at this example where we simulated data from 3 different classes. We said there's the red class, the blue class, and the green class, or I think A, B, and C. The red one is A, blue is B, and green is C. And these ellipses represent the multivariate normal distributions that generate our data. And so there is, for the red and blue, the x1 and x2 variables are independent, but for green, the green class, or the class C, there is covariance between x1 and x2, and that's why you see these ellipses are, the major and minor axes are not parallel to x1 and x2. And so the way we will calculate our probabilities require that we have estimates of the means and variances, and so we can just use the column means and the variances of our simulated data. And when we do that, these are the estimated multivariate normal distributions. These are, these fit the actual values a little bit more closely than the true. I guess these are the true distributions that were used to generate our data, and these orange lines are estimates of the distributions based on the data we have. So you can see, especially if you look at like the blue dots and the circles surrounding the blue dots, so you can see these ellipses circling the blue dots, are more closely aligned than, say, the quote the values of the distribution that was used to generate them. Okay, so just kind of a comparison of these things. And so when we give a test case, such as this point at 0, 0, and we say, hey, what class does it belong to? Obviously we can kind of spot it ourselves and say this is going to belong to blue. When we run the Bayes classifier, is it going to align with what our intuition says? And the answer is yes. So what we're going for is, what is the probability? So we're going to calculate the posterior probability for all 3 classes. We're going to say, what's the probability that 0.00 belongs to red? What's the probability that 0.00 belongs to blue? What's the probability that 0.00 belongs to green, right? So those 3 probabilities will add up to 1. How are we going to do that? Well, we're going to calculate the likelihood. The likelihood is basically the probability density of getting our point at 0, 0, given our estimates, that is these estimates, the estimate of the mean and the estimate of the variance that we calculated using the training data. So using we use the training data to get the estimates of what the mean of the red distribution and the variance of the red distribution. We used our training data to get the mean and variance estimates of the blue distribution. We used our training data to get the mean and variance estimates of our green distribution. And so we can use the normal multivariate normal PDF, which is this. And so if I say, okay, what's the probability of getting x new? I can do 1 divided by 2 pi raised to the d over 2. We are 2 dimensions multiplied by the determinant of the sigma matrix, which is our variance underscore a, again, just based on our estimates here, raised to the 1/2 power times e to the negative 1/2 of, transpose x nu minus mu, which is x bar, transpose times the inverse of the variance matrix times x nu minus x bar, and we get this. Okay, so we get 0.0008795,399. This is our probability density of getting 0, 0 if it comes from the red distribution, which is, this is a small number, which makes sense because we're saying basically what is the probability that these ellipses centered at the red dots would generate this point. And we're just saying, it's pretty far away from our estimated center of whatever it is, 2, 3-ish, something around there, not exactly 2, 3, but something around there. And we're saying, getting 0, 0, it's pretty unlikely to happen. We're getting a pretty small number here, okay? Now this is kind of a pain to have to do. This is exactly the PDF of the multivariate normal, and all I did was go exactly from this PDF to this. Thankfully, there is a function in R for calculating the density of the multivariate normal, DMV norm, and we say, okay, what is the density of getting our new point, 0, 0, if we have mean x bar underscore a and sigma matrix variance underscore a, right? And what is that number? And we get this exact same thing, 0.000879. It's the exact number that we have over here. So we can do it manually and get it. We can just use DMV norm and get the same number. This is our preferred way, okay? And also this just makes it easier. So, you might be like, is this cheating to use, some kind of function? I would say no. This actually makes your life a lot easier to, in terms of calculating it and knowing you did it right. And then also just being able to read it, it's a lot easier to read it this way as well. And so we're going to calculate the likelihood that the A distribution would produce the 0.00. What's the likelihood that the B distribution, the blue one, produces 0, 0? And what's the likelihood that the C distribution, the green distribution, produces 0, 0? Okay, and so we could see, okay, what's the likelihood that the blue distribution produces 0, 0? This one's relatively high at 0.165. And then what's the likelihood that the green distribution produces this? And that one's found to be very unlikely, 1.6 times 10 to the negative 5. Okay. One thing about densities, can your density be higher than 1? It can be, depending on the size of your variance. So when you have it's that the integral of the integral of the density over the entire domain has to integrate to 1. But if you have if it's very concentrated in one area, the individual density can be very high. So densities can be over 1. Okay, PDFs can produce values over 1. PMFs cannot, because the sums have to add up to 1, and you have a discrete number of terms. But yeah, densities themselves can be 1. Cumulative distribution functions cannot go over 1. They will equal 1 at as you go to infinity or whatever. Okay, but anyway, we have these likelihoods. In our case, our density doesn't go over 1. It's 0.165. That's probably what we have. The prior probability is, what is the probability that, before we even look at the data, what is the probability that a new observation belongs to class A or class B or class C. This is, I guess, depends on our prior knowledge or our test cases. So if we say, hey, you know what, in our test data we have 90 observations, or training data we have 90 observations, and 30 of them come from each of these three classes, and we're kind of assuming each of these three classes are equally represented, then we can just use our prior probabilities and just set them all equal to 1/3 each. Okay. But again, if you had a different scenario, we did like this, the marble factories, and we said, factory A produces half the worldwide marble supply or something, and then you would change your prior probabilities. Here we'll go ahead and use 1/3. Now, technically, because we're having the same value in all of these things, they're all going to kind of cancel out when you sum them up and divide by the marginal. So, it's not like in this exact scenario, it's not necessary to include them, but we'll go ahead and include them just to kind of make sure we're following the formula correctly. And I don't want to confuse anybody by like ignoring them in this example, but saying like, oh, you got to think about it here, because they're all equal, they just cancel out. But yes, in general, they might not always be equal, and so you want to include these prior probabilities. Okay, and then the marginal probability, the value that goes into the denominator, which is there so that the sum of the numerators, the sum of the probabilities add up to 1, is basically going to be the sum of the numerators. So I'm going to do the likelihood times the prior for class A, plus the likelihood times the prior for class B, plus the likelihood times the prior for class C. So that is our marginal probability. And we go through and we're going to say, okay, what is our posterior probability? We're going to do our likelihood times the prior divided by the marginal. So I do likelihood times the prior for class A divided by the marginal. And these are our probabilities. We get a 0.005, so around 5/1000ths, about 1/2%, that it belongs to class A. 0.9946, so around 99.5% probability that it belongs to class B, and then something very close to 0, 9 times 10 to the negative 5, so I guess 1 in 10,000-ish that it belongs to class C, the green, okay? And that aligns exactly with what we saw, where we put a test case at 0, 0, and we said, what is it, red, blue, or green? And, it came back 99.5% probability that it belongs to blue. Okay, but again, not 0 probability that it came from red, and also technically not a 0 probability that it came from green, but much, much, much lower, relatively speaking. Okay, what about this? Here is a new test case that we're going to put at 6.2, and if you had to guess where it came from, what would you say? Red would probably be the most likely. Which one would be the least likely to generate this one? The blue. All right. So when we look at our results, we want to say, okay, we expect red to be the highest, blue to be the lowest probabilities, and we'll go through and so we just do. Here I just did it all on one slide. Okay, so we have the likelihood by using DMV norm. We're going to say the priors are all 1/3. The marginal is the likelihood times the prior for all three classes summed up. And so the posterior probability that it belongs to class A is the likelihood times the prior divided by the marginal. We get around 79% class A. For class B, likelihood times the prior divided by the marginal is on the order of 3 times 10 to the negative 9. So a really, really improbable value. And then the probability that it belongs to class C is around 20%. Okay, so around 80%, 20%. For class C, almost 0 for probability of class B. Okay, is this all right? How our Bayes classifier is working? I think I do one more test case, and what do you feel about this? So here we're going to get fairly similar values for red and green, okay? And then we do that and we get at, after doing the calculations, we get around 39% A and 61% B, C. And then again, something close to 0 for class B, the blue class. Okay, and then, and then, so here, I was just trying to like play around and find like values that are like at the intersections of all of these things. Okay, so if you do have a point right here, okay, at kind of the intersection of these things, we get something around 30 something percent for all three classes. Okay, so this is at location 2.53, 0.37, for these three classes, but they're all very kind of probable here. Okay, and so this page is our summary page saying, we just do the likelihood times the prior divided by the marginal, and I hope this kind of makes sense regarding how we get these things. Okay, let me go ahead and give you your first view quiz answer for today, which is letter D. D as in dog. D as in dog is our first view quiz answer today. D. Okay, so now we'll look at the naive Bayes classifier. Naive Bayes classifier is pretty much the same thing as the Bayes classifier, except we bring in what we call the naive assumption, which is a bad assumption, but it also it makes our life easier. And sometimes we do things that are wrong, wrong, like there's no moral statement here, but we do things that we know are not accurate. We do things that we know are less accurate, but for the sake of making our life easier. And so we do that. So the naive Bayes classifier says, you know what, having to work with a multivariate Gaussian and estimate the covariance things, sometimes, that can be tricky. And can I just treat x1 and x2 as independent? Can I just treat our incoming variables, x1, x2, however many x variables you have, can we just treat those all as independent of each other? And the answer is, yeah, you could do that. It's not accurate, okay, but it will make our life easier because now you no longer have to estimate covariances, right? So when you're estimating the properties of your distribution, you just need to estimate the variance of x1, the variance of x2, and you don't need to estimate the covariance of x1 and x2. And depending on your data, you might not even have enough points to accurately estimate the covariance between x1 and x2, or this especially gets more important as you have larger like data with more x variables, okay? And then perhaps if you have like not a ton of observations for each of these classes, right? So let's say you have like 10 different classes, class A, B, C. You have to get, variance estimates for all of your x variables for all of the different classes, and then you would have to get covariance estimates for all possible kind of covariances for all possible classes, and you might not have enough data to get accurate values for each of these things, and so you could end up, especially if there's like a weird fluke in your data, it could really throw things off too. So the naive assumption just says, let's just pin all of the covariances down to 0. And we know, that's not going to be great, but a lot of times it works out, okay? A lot of times it works out. So what happens is your multivariate normal distribution can be decomposed into a product of univariate normal distributions, okay? So your multivariate normal, now that we're treating all of the x variables in this thing as independent, we can say, okay, the joint distribution of this value at x1, x2 is now going to be the product of the probability of x1 times the probability of x2, okay? So all this is saying is, here's the PDF of the multivariate normal, this is now equal to, this is the PDF of a univariate normal, just a regular normal density for, and then, you know, you're going to have however many dimensions you have, it's going to be the product of all of those univariate things. So here is our same simulated data that we have from before with red, blue, and green. And to estimate this, we are going to calculate our estimates for each variable, but just one, for each class, but just one variable at a time. So I'm going to calculate the mean for x1 for class A, and so this is going to be x1 bar for class A, and that's just the mean of basically our XA observations, column 1. I could have also used column means here as well, but just this is to emphasize we're just doing one column at a time. And then the standard deviation or the variance, I'm just going to do the standard deviation of the variance of one column. Okay, so each of these are scalars, whereas way back here, where did it go? Okay, these things you put in a matrix with 2 columns, you're going to get a 2 by 2 matrix for this variance. Okay, but here I'm just going to do the variance or the standard deviation for each of these things, and I'm just doing one column at a time. Okay, and so when you plot the contour lines, this is what the contour lines end up looking like. All of the and so for red and blue, it's not that big of a difference. For the green one, we can see this is kind of like wrong. So it's treating x1 and x2 for the green distribution as independent when there's high covariance in real life. So if I compare that to the estimates from the multivariate normal distribution, we can see, okay, pretty close alignment for red and blue, but here we can see it's pretty far off. So these are both like the estimates based on the data that we have, and we can see there's a difference. It turns out though that even though this green thing is like way wrong, the estimates that we get using the naive Bayes classifier aren't wildly off either, right? After you take everything into account and you get a class estimate, they're going to be different. The values are going to be different, but generally you're getting your classification correct. Okay, so this is what we have. So we're going to put in a test case at 0, 0. All right, and so we go through. Again, we're going to calculate the likelihood. We're going to calculate the prior. We're going to get the marginal by doing the likelihood times the prior for all of them and summing them up. The only thing here is that the likelihood, we're going to calculate this as the product of 2 2 univariate normal density functions. Okay, so rather than using the density of the multivariate normal, we're going to use d norm, the density of a univariate normal. And we're going to do d norm for x1 multiplied by d norm of x2. And that's what we will do. So the likelihood of that it belongs to class A is going to be d norm of basically our new observation, variable 1, x1, using the mean of x1 for class A and the standard deviation of x1 for class A, times d norm of basically x2, using the mean of x2 for class A and the standard deviation of x2 for class A. And I do the same thing for class A, class B, and class C. All right. So as the product of univariate normal densities. Now, this is so in your homework 4, the next homework, you will have to write a function that does naive Bayes classifier for the IRIS data set, I think, and just be careful. Make sure you use d norm to get your PDF, okay, and don't use p norm, okay. So it's sometimes students, if you use p-norm, you're going to get all the wrong answers. Okay, p-norm's the cumulative distribution function. That's not what you want. You want to use the normal density, which is d-norm. Okay. Okay, so that's what we have. All right, is that okay regarding getting the likelihood? Okay, prior is going to be 1/3 for all of these things. Marginal is likelihood times prior for the numerator. Again, they all cancel out, but here, we'll keep them in there. And so basically, I'm just going to take these numbers and then scale them up so that they add up to 1. And when you do that, you get around, you get likelihood that or the posterior probability that it belongs to class B is the highest at around 94%. When we did the multivariate normal, it was like 99.5%, and now we're getting 94%. And then actually class A and class C are now in different order, so you get different things, but that's again because of our naive assumption here. All right, but that's what we have. Okay. So here's the naive Bayes classifier. Just you take your multivariate normal and you turn it into a product of multiple univariate normals is what we do for the naive Bayes classifier. Treat our predictors as independent. Okay. Let me go ahead and give you your second view quiz answer, which is the letter B. B as in bear is our second view quiz answer. All right, and so here's, I don't know, I thought a fun application. Fun is always debatable, but the naive Bayes classifier can be used for, more complicated applications, I guess. For example, you can create a document classifier using the words that are spotted in a document, okay? So the naive Bayes classifier can be used as a document classifier, and we use the naive Bayes classifier because what it's going to do is it's going to assume that each word appears independently from the other words in the document, okay? And that's just not going to be true, but it makes our life easier, right? So we know in real life there are certain word combinations or certain, like, some words are more likely to appear together, and other words are not, right? So here I said like white and house are going to be more likely to appear together, or red and light, or something like that. All right, and it doesn't even have to be like two adjacent words, okay? It could just be like, if your document has the word player, then your document's also more likely to contain the word game, okay? Or team, or something like that, right? And probably, less likely to, contain, I don't know, whatever, right? And if your document contains the word Bayesian, it's probably more likely to contain the word statistics or something like that, right? It would be really hard if you think about like all the possible words in the English language. So usually when you think of, for this, all of your X variables, you'll basically have a count of each word, okay? So, you're going to have maybe like, if you say you have 80,000 words in the English language, I don't know how many words there are, but let's say there are 80,000 words that are relevant to your thing. You now have 80,000 X variables coming in, okay? Most of them are going to be 0, okay? Most of them are going to be 0, and then you're going to basically, X1 will be how many times does the word A appear? X2 will be how many times does the word, I don't know, AA, whatever the next word in the dictionary would be, right? And then, X3 will be how many times does the word aardvark appear or something, right? And you have basically this vector of how many times each of these things do. If you wanted to do not the naive assumption, then you'd have to calculate the covariances between all of these things. If aardvark appears in your document, how does that affect the probabilities of any other word, right? Calculating the covariance between this word and every other word, that's going to be hard. So we don't want to do that. So we're going to use the naive assumption, okay? We're also going to use something called the bag of words model. I don't know if you've heard of this, But the bag of words basically says we're going to treat a document, and the word document is a very loose term, okay? It could be a literal document, like a newspaper article, but it could also be as simple as like a sentence, okay? And basically, you treat it as a bag of words. So just, I don't know, just imagine like a cartoon where like, they hit the screen and then the words just fall down, and, like you shake the screen or something and then the words on the page just kind of fall down at the bottom, and you just treat it like, okay, now we have a bag of words, okay? And then the key thing about a bag is that items in a bag don't have any order, right? Like if you reach into your backpack and I say, give me object number 3, like that's a nonsense statement because there's no like, this is the order of items in my bag, okay? So the order of words don't matter, order of words in a bag, right? Versus like a list, there's an order there, okay? So the only thing that matters is just how many each word appears, and the order of words don't matter. Now, there are major limitations of the bag of words, and that is, in English, the order of words do matter. So if I have the document, it is bad, it is not good, the bag of words will turn it into account, and it'll say it shows up twice, is shows up twice, bad shows up once, not shows up once, and good shows up once, okay? If I have another document which says the exact opposite, and it says it is good, it is not bad, okay, the exact opposite of what the first document is saying, this will have the exact same count of words. It also has it also has is twice, it has bad once, not once, and good once. And so our document classifier, which uses the bag of words model, will say both of these two things, whatever it's saying, or they're saying the exact same thing, okay? And we know that's not correct, okay? And so for a while, I don't know if this is still popular. There's, for a while, this concept of sentiment analysis was a popular thing, and it was the idea of like, you could take somebody's tweet or somebody's like movie review or product review, and you could attach a sentiment, and you could say like, oh, this person feels positively about the subject, or this person feels negatively about the subject. I always thought these, I don't know about always, but if you use a bag of words model for sentiment analysis, my opinion is that the analysis is going to suck, okay? Is that because, these two things have opposite sentiment, a bag of words model is going to say they have the same sentiment, okay? So if you don't take into account the order of especially words like not, which negate whatever it was saying before, it's gonna it's not gonna be able to detect things, okay? And certainly, and in a lot of cases, the word not is treated as a stop word, meaning like we just throw it away. And so, that's going to be a problem. All right. So here's a very simple example. When we do some kind of document classification, we require what's called a lexicon, or just basically a list of all the words and all the probabilities associated with each word. Okay. A real lexicon might have somewhere between 10,000 and 80,000 words, basically however many words are that you want to kind of include in your vocabulary. And each of these things, and the lexicon could be designed for dozens of possible document categories. So if you want to, do like a news article, classify a news article, you might have, these are the 20,000 words that we're looking for, and these are what we think the probabilities are if the document is about politics, or these are probabilities if we think the document is about sports, or the document is about some other subject. In the lexicon, the sum of all the probabilities must sum to 1. So all of your numbers will be really small, right? Because you got 10,000 of these things. The 10,000 things have to add up to 1. And something like that. Here I have basically our different words in a column, And so the columns will add up to 1. The rows will not. Okay? This is a very, very, very simple, exaggerated lexicon. We're going to say we have a total of 8 words in our entire English vocabulary. And we have 2 classifications. And we're going to say our document can be about fairy tales, or a document can be about chess. Okay? And we might have words like the king or the queen or princess, knight, rook, good, evil, and bored. And so what's the probability? So, if we're talking about a fairy tale, you might have king. You might have, if you're talking about chess, king also is a high likely word. Okay? Same thing for queen. We're going to say queen has high probability of showing up in fairy tale, high probability of showing up in chess. Okay, the word princess is, very unlikely to appear in a discussion about chess, right? I don't know. Okay, whereas princess is very likely to appear in a fairy tale. Okay, knight could appear in both a fairy tale or in chess. Okay, the word rook, very unlikely. I don't know, is unlikely to appear in a fairy tale story. Much more likely to appear in chess. Okay, perhaps the word good could appear in both. Okay, you can have good versus evil in fairy tales. A move could be considered good. Okay, maybe the word evil, though, we'll say has a decent probability of showing up in a fairy tale, whereas it'd be quite strange for the word evil to appear in a document about chess. That we're talking about a board game, so something like that. Okay, and then the word bored, likely to appear in chess, but not so likely to appear in fairy tale. Okay, so this is, again, silly example where you have like these common words between fairy tale discussions and chess, but certainly certain words will be an indicator that this is part of a fairy tale versus a discussion about chess. Okay, so if this is our lexicon, how do we classify words? Oh, okay. So, this is just a side story about training your lexicon. If you don't have the lexicon to begin with, you would build it up by like scanning a whole bunch of documents. You would just go through, I don't know, a newspaper's archive or something, and say, okay, these were stories about politics. These were stories about sports. These were stories about entertainment, stories about business and things like that, or whatever else it is. And then you have to, you scan all of these things and you say, okay, when it was in politics, words like senator and representative and democracy or whatever, shows up frequently. And if it's about sports, words like player and team and game, those show up, more frequently. Okay. Also common to remove words like the, is, to, a, words that show up frequently but don't provide any kind of contextual information, right? If I tell you the document has the word the 50 times, it's not going to help you classify what category it belongs to. So a lot of times we just throw those away. Those are called stop words. Okay, so anyway, let's say we decide to use a naive Bayes classifier here. And so let's say this is our sentence. The evil queen sent the evil knight to capture the princess. Okay, so is this a sentence about chess or a sentence about fairy tale, right? It's a bad sentence, but just whatever. Okay, so basically Bag of Words says, okay, let's look at the words in our lexicon and let's count how many times each of those words appear. So queen appears once, princess appears once, knight appears once, evil appears twice. Okay, capture could have actually appeared in both fairy tale or chess or something like that. But okay, so this is what we get. And so the likelihood is, what's the probability? Because our posterior is what's the probability that it's fairy tale given these words. And so the likelihood is what's the probability of getting these words if it were a fairy tale story. And so we're going to say, okay, what's the probability of getting queen if it's a fairy tale? What's the probability of princess if it's a fairy tale? Knight if it's a fairy tale? And evil if it's a fairy tale? And so these numbers, queen is probability 0.2, princess is 0.25, knight is 0.2, and evil is 0.11. Evil shows up twice, so we're going to do 0.11 squared, and this is the likelihood of, our sequence of words. Not sequence, our bag of words, I should say. Okay, we do the likelihood calculations for chess, okay? So if it were chess, what's the probability that it's queen? We get 0.2. Princess for chess has a very low probability of 0.01. Knight in chess has a probability of 0.15. And evil in chess, again, has a very low probability of 0.01, and it appears twice. So our total likelihood for this document is much, much lower at 0.00003, okay? The next part, we do, sorry, I didn't check the formatting here, but we'll have prior probabilities and we'll say prior probability is 0.5 and 0.5, equal chance of it being about fairy tale or chess. But again, if you have prior information and you have, I don't know, you're going through your, relative's house that they have books about fairy tales or chess or something, and maybe they were a chess fan and most of their books are about chess. You would adjust this, right? And you'd say like, okay, 80% of the books are about chess and the remaining 20% are fairy tales. It's a weird taste of books, but that's what we have. And so your marginal would be the likelihood times the prior plus the likelihood times the prior for all of these things. Sorry, got cut off over here. And so our prior is 0.5, so we take our likelihood times our prior, our likelihood times our prior, and we get this really, really, really I missed some. Wait a minute, something happened here. Something doesn't quite add up right. Okay, I think I messed up some number here. Okay, well anyway, just pretend the math here works out, okay? I think it said like e to the -9 or something, and I tried to type in the zeros myself, and so maybe I didn't do it correctly. So we're going to do likelihood divided by likelihood times the prior divided by the marginal to get our posterior, and now I'm questioning whether I did my math correctly. But we're going to get something like 99% that it's a fairy tale, and less than 1% that it's about chess, using this kind of thing. And again, this was just a silly example with two possible classifications, but depending on the quality of your training data and how many categories you have in your training data, you could build up your lexicons, which again is no trivial task, but you can build up your lexicons by scanning all of these documents and getting word counts and then running them accordingly as well. Okay, let me give you your last VueQuiz answer, which is the letter A. A as in apple. A as in apple. Okay. So anyway, I thought this was kind of a fun idea for the naive Bayes classifier. And again, if we were not using the naive assumption, we would have to say, okay, what's the covariance of getting, the word king and queen appearing together? And we'd say, oh yeah, there's high covariance there. What's the word, covariance between king and good appearing together, or king and evil? And now some of these things are a little bit more murky and tough to figure out. And so, trying to figure out all the covariances between all of the words in the English language would be a, very challenging task to do. So we avoid it, and we just say, let's assume all words are independent, which, again, not correct, but certainly makes our life easier and works out okay in a lot of cases. Yeah.
The VueQuiz answers were not.
The VueQuiz answers were wrong?
Yeah.
What did I tell you?
DBA.
DBA?
Yeah.
That's not what that's what I have here. Okay. Oh, gosh. All right. Okay. All right. We'll fix it. Okay. Just enter the letters I said, and then I'll go back and I'll fix this thing for you. I know. Okay. My bad. All right.
So you got the other thing.